Our next speaker is Mr. Nikhil from Intel, and he is going to talk on AFXTP. Mr. Nikhil Rao is a software engineer at Intel, and he is currently working on network packet processing software at Intel. He has worked on system software for a variety of product lines, including HPC, graphics, media, and media processors. Nikhil likes to beat the traffic by cycling to work and is a Carnatic music buff side as well. So let's put our hands together for Mr. Nikhil.
Yeah, hello everyone. Actually, I'm here today to present some work that is being done from by our colleagues in by our team in Sweden, and they're not able to be here with us today. But we thought their presentation and or the work that they did was interesting enough that we could share it at today's DPDK summit. So it's about fast packet processing in Linux with AFXTP, and that's AFXTP itself is a bunch of just an abbreviation, or so it doesn't tell you much about what it is. But let's get into it. So for people on the back, I don't know if you can see the entire figure. Well, on the left-hand side, we have this current model today with we have the L2, some application, some packet processing application. We have a NIC PMD, and then we have direct access to the NIC, right? So that's the model that we all as DPDK programmers have learned and are using on a day-to-day basis, right? And on the other side, we have a model which is sort of has a is similar in the sense that you still have a PMD, but it's almost a hardware independent PMD, right? And you have all your hardware management being done in the kernel, so being done by the kernel driver. So essentially, this is a mechanism where that's providing better security, isolation, and so on. And I think it's for certain people who are for certain use cases where fault tolerance, robustness, availability are of paramount importance. Those use cases, those users would actually prefer the model on the right, and there may be a slight performance penalty that they would be actually willing to pay. So, and for again, this is, we hope that we or this work actually intends to provide the same performance that we have with DPDK PMD and user space packet processing and so on. At the same performance, with all the hardware managed by the kernel. And so what is being done here is essentially zero copy to user space in the most optimal configuration, and depending on availability of hardware support. But there are also some fallback methods that are not as performant, but still give you better performance than the existing mechanisms in Linux, right? In Linux, we have the AF packet interfaces that you can map the packet buffers directly to user space and operate on them. But there are certain optimizations that these folks have identified, and even in cases where there is one copy, actually we get better performance than the currently existing Linux stack. And so the other advantage that we have come to love with DPDK is the is using huge pages for our packet processing, right? So that reduces TLB pressure and does a bunch of good stuff. And so we also retain the same advantage on the in the work that is being done here. So we thought, I'll just as I said earlier, we had this work is based on something in Linux called XDP. It's called it stands for Express Data Path, and essentially Express Data Path is a mechanism to run secure code that is injected from user space into the kernel and run it at the um, earliest point that you can possibly run some code, right? So essentially, it's just after the NIC has done, after the packets have been DMA'd to memory, and you get to run your code that is injected from user space. So it's validated through some mechanisms and is guaranteed to be secure and so on. And you can use it. It can look up tables, decide next actions, modify the packet, and sort of do some actions like drop the packet, forward the packet, just relay it onto relay it onto the local stack for processing and so on. So that is in a nutshell XDP. I mean, it's a lot of work has gone into XDP, and it's sort of gaining popularity currently. And essentially, XDP relies on, for the most performant case, the XDP relies on the NIC driver to support a few callbacks. The first callback. So these callbacks essentially allow you to, first of all, install that program so that you can, or activate that program so that the XDP program that's actually what we call in eBPF, or extended Berkeley packet filter syntax. It allows you to install that program as in the code path, and then there are a couple of other callbacks that allow you to sort of transmit packets from the receive page, directly. If you decide that you want to forward the packet then it allows you to sort of transmit the packet from at the highest layer, right, through and then these two, that's the XMIT and the XDP flush. So that's in a nutshell what XDP is about. And this sort of this work that is being presented today is based on XDP. There were previous versions of it that were sort of extensions of the AF packet interfaces. So AF packet is version 2, version 3, and a version 4 was created. But based on feedback from the kernel community and so on, the work was then retargeted to be based on XDP. So this is what it looks like today. Again, you have the normal, in the green, you have the stack packets being processed by the kernel stack, like always. And you have this XDP sort of hook there, which sort of decides which way the packets are processed. And then you have the AF XDP socket that's exposed through libc. So you go off, and when you go off and create your socket, you declare that you want an AF XDP socket, and you have some other mechanism to load this XDP program. And then off you go. Almost you sort of allocate some user space memory. Again, register it with the NIC. And then get started, right? And so the idea here is the APIs that are being used by this application are again sort of platform independent APIs. So they sort of are not dependent on any NIC, right? And earlier today, someone had a question about the Realtek NIC, and there's no support for it, and in DPDK and so on, right? So assuming that it's supported, there are some extensions that are done to that NIC in the kernel, the NIC driver in the kernel, then you can sort of get this fast processing support. And from DPDK's perspective, like I showed on the first slide, right, that you could actually construct a PMD and sort of give the same DPDK API to the application, and that's actually been already done. There's a AF XDP PMD been posted to the mailing list maybe around last week or so. So even that's the enablement is also progressing quite well. What else? So the goal is to hit line rate on this, and we are still quite ways away from here. But just to provide some context, the AF XDP work the AF packet version 4 work that was done earlier was able to get quite close, right? So this code right now is sort of unoptimized and so on. So there's a lot of optimization work that's going on as we speak, and so the goals seem to be realistic in that way. So this is the sort of the data path, and so the packet starts off, it lands, there's a DMA engine in the NIC, and it's actually been DMA to the application's memory, right? Provided the application memory here is registered with the NIC and so on. And we have set up the right filters using something like ETH-tool, for example, to redirect a particular kind of traffic to this queue, right? So there is a particular queue that's associated with this socket, and essentially there's some setup that happens to make sure that the right packets are being directed to that particular queue. So the packet has actually arrived in application memory from the wire, assuming that the application memory has been registered and so on. And so it triggers actually the typical code path of the interrupt handler, soft IRQ executing, and there is this XDP hook that executes, and then that has some checks in there, and it actually activates a zero copy receive path, right? So in the zero copy receive path, actually all that is being done really is take the index of this particular application memory page and add it to this mapped RX ring. So the application is presumably sitting there polling for new packets, and it gets access to this particular new packet that's landed in its memory. And then once it's done with the processing, it would actually so this actually would get transmitted. Presumably the packet would get transmitted and so on. And so the transmit works in a very sort of analogous way, where you have a transmit ring that is mapped to user space, and sort of you notify the NIC to transmit the packet. Once the transmission is done, the NIC is the packet is returned to the application, and then the application loans the packet back or returns the packet back to the receive path, so that new packets can land there. So that is in a nutshell how this pipeline runs here. So there's a couple of modes in which this operates. One is we start with the slowest mode first, and that is the what we call as XDP SKB, where actually the copy is happening sort of later in the stack. When the packet has been received, there is no support in hardware. The network stack has formed the socket buffer, and but then there is still some XDP hook that indicates that the packet should be transmitted to, or be mem copied actually, to the application buffer. So sort of this is the slowest path, but it's still better than the AF packet alternatives that exist currently. Then the other two, the XDP_DRV option is faster, but there is a mem copy involved. So this is sort of not the zero copy option. So that works with the currently existing XDP support. So if you have a NIC that is enabled for XDP, you should be able to, in theory at least, should be able to use this mode of operation. And then finally, the the performant option that is available is zero copy, and that actually just does DMA to the application buffer, right? So some of the driver support specifics that are sort of required here, one is sort of we begin with enabling the zero copy, and then there is some special handling of the transmit that is required in the driver. Essentially, the application has indicated that a packet is ready to be transmitted, in the in its TX ring, and then it issues this particular system call today that all it does is get into the kernel and invoke this hook from the driver, and that actually triggers the transmit interrupt for the driver, and then the driver pulls the packet and converts it into a descriptor. Doesn't pull the packet actually, creates a descriptor for the packet, transmit descriptor for the packet, and schedules the packet for transmit. And that's invoked in the send path. And the flush is similar in the sense that, again, it's a batch processing sort of philosophy. And so once you have a bunch of descriptors queued up, then you invoke the flush, which essentially goes and updates the tail pointer, right? So this is done in such a way that the core, there is some core infrastructure, and that's separated from the specifics of the particular NIC that is being used on the platform. And again, to make sure that the NIC code is not involved with the intricacies of all these modes that we described previously, right? So there's an abstraction that is created in the NIC, or some set of callbacks that are created in the NIC for, they're called buffer allocator callbacks. But, for example, in the zero copy case, it's actually receiving, or it's pulling packets and sending packets back to that particular user ring that we talked about, right? So these are a set of callbacks that are needed in the NIC for enabling this feature. So the security, it's more or less in line with the typical process level security or isolation model that is available in Linux, right? Very standard things. The descriptors, the hardware descriptors are not exposed to the application. So it's only a sort of a ring that has some buffer indices that is exposed to the application. So it's ultimately it's the NIC that is dealing with the hardware descriptors and so on. So there is security from that aspect. And with respect to packet steering, right, we are relying on some features in the NIC. And if those features are not available, actually it should be possible to introduce XDP program or an eBPF program that actually allows you to redirect the right traffic to the particular queue, right? So the security model is somewhat or almost very standard Linux security model, right? So as I said earlier, this is actually been recently posted, the AFXDP PMD, and it is sort of hardware independent. It relies on some libc it relies more, almost entirely on sort of libc calls. And the idea here is that all your hardware management is moved to the kernel, and DPDK here is purely used as a shared library, right? And the reference to SRIOV is, obviously because you have there are a lot of issues created when you have these PMDs that are that are manipulating virtual functions in your VMs, and then you have a PF driver, and those two are not synchronized and so on. So you sort of bypass those difficulties in this model. So this is the usage model in terms of the application calls that are needed to enable the AFXDP sockets. So you start off by creating sockets, you allocate memory, and then you register it with the kernel for zero copy. This sort of mechanism is constantly evolving, but fundamentally the operation still exists, that you register, where you register memory with the NIC and with the socket. And this is very similar to what happens in other infrastructures like RDMA, for example. Then the next step actually allows you to map the TX-RX rings into user space. And that is based on the, that is the medium of communication between the application and the NIC here, right? And then the next step is you post your receive buffer so that you can start receiving packets. Then you create the, you sort of bind the socket to that particular queue that you're receiving packets on. And then the next is just a, sort of the L2 forward loop where you process the packets and, send them for transmission and so on. So it's a very, at least the sample code that I've been working with and sort of helping these guys with some changes, it's been like very simple to work with. And this is the sort of the interesting part, and that is the they published. There was a paper actually. There was an RFC published on the Linux kernel mailing list very recently, and they also did a talk on the at an open source conference called FOSDEM, where they talked about these results and so on. So this is kind of the experimental setup here, and obviously, you may have noticed that in addition to the app core, there is also an RxTX core that is sort of handling the interrupts back from the NIC in this. And so that's like the penalty that you pay for going along with kernel support. But at least you are getting sort of very good performance in your application, right? So that's the experimental setup, and sort of these are the results that they achieved. So these are sort of very sort of code is very new, fresh, and so there's a bunch of optimizations that they can do. For example, as I said earlier, there was a AF packet version of this that was posted some time back, I think in November. And at that point, they were able to reach 33.7 in what they call RX for the RX drop case, where just receive packets and then you're sort of recycling the buffer. So it's actually quite encouraging, right? And so some of the so we'll get into some of the future work that they have set aside for performance optimization. But one of the examples is basically adopt some of the same techniques that we use in DPDK with respect to batch processing of packets, right? So when you process a packet in that particular, when you receive a packet and you get the interrupt for it and so on. So it's all sort of with every packet runs through the whole code flow, right? So they are looking at some optimizations that you can make better use of the instruction cache, right? So that's the work, and actually there were some people asked me during some discussions, what about the PMD metadata, right? Today, I didn't mention that anywhere in the presentation, right? So how does that get scraped from the NIC RX descriptor and put into the sort of the RT-MBUF structure that we are all familiar with? So that there are some ideas on how to do that, and sort of shouldn't be much of a performance penalty, and that uses this XDP. Again, using a XDP program or an eBPF program, you could sort of get that thing done in a without sort of getting into the compromising with the security of the system and so on. So that's it for today. I hope this talk was useful, and if you get a chance, take a look at the Linux kernel RFC that's been posted, and also the AFPMD DPDK PMD code that has been posted to the DPDK mailing list, and maybe you can get to contribute with something, right? And obviously, there's a lot of people actually who helped with this. Maybe over the last couple of years almost, within Intel and also outside Intel, companies like Red Hat and so on. And that's time for questions.
Hi. Could you go to the security and isolation slide?
Sorry. Sure.
Yeah, you said user space cannot read or write any packets from any other processes unless packet buffer is explicitly shared.
Right.
So wouldn't it be possible for my XDP or eBPF program to forward all of those packets to that particular socket, thereby reading all the traffic that comes on the NIC?
I mean, if you are allowed to execute that eBPF program, right, then certainly yes. I mean, we are operating within the security model of whatever eBPF XDP provides, right? So, if it allows you to do that, then yeah, you can. I mean, there's nothing in this to bypass that. So we're just playing with with the support that's already available in the kernel, right? I'm not familiar with that familiar with the XDP and eBPF things and so on. I haven't written a program myself, so I can't answer your question to that level of I can't answer that question specifically. All I can say is it still plays within the eBPF security model. So if something is broken there, we ought to fix it there, right?
Thanks.
Yeah. So on the same slide in the first bullet, so when you say user space cannot crash the kernel, so in a later slide you still talk about the descriptor rings being shared between user and kernel, right? So then that means user space has an opportunity to.
Yeah. So I wasn't actually I should have emphasized that point, right? So this is one place where we talked about the TX RX rings, right? So this is the actual NIC descriptor ring. Should I put some text here? But so that is out of bounds for the user space, right? So that is controlled by the NIC driver. Okay, and so these are just what is available here is just buffer indices in the RX and TX rings. So and these buffer indices point to pages that were already registered by the application with the kernel, right?
So you're saying the application does not have direct access to the descriptors?
No. So the application only has access to those particular rings, right? So there was some code example where I showed, two particular socket calls that you can, one to get access to the RX ring, one to get access to the TX ring.
Correct.
Right? So those calls map those sort of virtual descriptors into user space.
So is there some code which is syncing the NIC ring and that ring?
Then? Yeah. So as I said earlier, right? So when you receive packets, right? The XDP infrastructure, right, has to sort of there's an initialization phase where you have to sort of fill in the NIC descriptors, right? But once you're in steady state and you're handing off completed received packets to user space, right? You're depositing in that particular ring, right? So then there's a callback that the driver invokes, right, to replenish the RX ring here. And that callback is essentially getting its packets from that particular return ring.
Okay.
So that is the mechanism of how the
so
ring is progressing.
There's still some kernel code which is accessing those rings, right?
Kernel code that's accessing those rings, yes.
Correct. So if application has the ability to write to that memory, then you can always lead the kernel somewhere else.
I mean, those descriptors are very simple, right? Those are just buffer indices, and the kernel is very easy for them to
no pointers.
Validate.
No pointers to data buffers.
Okay. No.
Hey, Nikhil. Hi.
Yeah, hi.
Yeah, thanks for your presentation. Quite informative. I had a question with regard to. I had a question with regard to RSS. The predecessor for XDP AF packet had something called a fan-out group, right? So in this case, if I were to have multiple rings, is there a provision to map rings individually to different cores and do I/O on rings?
So, I mean, as far as I know, you can create multiple rings, and I mean, I don't get the specifics of the question that you asked. Maybe you can. I don't know, maybe you can take it offline.
Yeah, sure. I'll catch up with you offline. Thanks.
From a point of view of getting packets to user space applications, probably like some IDS or IDPS. So how will this solution differ from a DPDK based solution or a netmap based solution? I mean, we are bypassing the kernel stack in this case also, right?
It's so there are certain environments where you want the hardware initialization and support to all exist in the kernel, right? You don't want to be loading user space, drivers, and so on. So in those cases, but until now, if you had that requirement, then you have always paid quite a large performance penalty when you wanted to use the network support from the kernel and so on, right? And so in this case, you are almost, we are aiming to get you the same performance as the DPDK PMDs, but using the hardware support that's already present in the kernel, right? And also then your user space layer becomes a lot thinner. It doesn't have, a plethora of PMDs, Ethernet PMDs in user space. You just have a very simple PMD, or, your application just talking to the rings directly, whatever it is. You just depend on the hardware support that's already available in the kernel, right? And even today, what is there in the AF packet interfaces, for example, I don't think it would allow you to use huge pages as a target for your packet buffers. So that's again a very important consideration, and that's something that DPDK facilitated. So it's the same support that is being provided through this interface. So
Yeah, but netmap and AF packet v4 are almost similar, right, in that case?
I'm not sure about the specifics of netmap, but AF packet v4 was essentially this work. v3 is what is there today, but v3, you're mapping packet buffers into user space as opposed to providing, huge page memory to the NIC. So, yeah.
We'll take one last question, please.
So yes, for supporting zero copy, we need to DMA directly into application memory. So is it supported by some special hardware, or all general NICs are supporting this?
So there are some. So essentially, what is happening in there is we are registering the page with the kernel, right? And so those pages are pinned, right? And then the NIC is able to typically DMA to any memory that is pinned and sort of DMA mapped to the kernel. So we have so there are some extensions in the NIC that allow you to DMA map these pages and sort of manage those operations. But it's not very, it doesn't require any specialized hardware on anything. Those are just callbacks in the NIC, yeah.
Yeah. Thank you so much, Nikhil.
Yeah, thank you.
It was a wonderful, informative session.